Hello, welcome back to my channel, and this is the first video in quantum mechanics lecture series where first thing we're gonna learn about is Schrödinger equation. So what is this Schrödinger equation? What does this give us? I'm not gonna derive the Schrödinger equation, we can derive later on, but we're gonna understand it more conceptually and mathematically what give us and what is this wave function is. So before going into quantum mechanics, let's review our goal in classical mechanics, what we do in classical mechanics, and can we replicate that to quantum mechanics. So our goal in classical mechanics is to find this x, which is a function of t, and if you know this position at any time t, you can find the velocity because this is just a derivative of position with respect to time, and if you know the velocity, you can find momentum, and you can also find kinetic energy. So if you know the position at all time, you can find all these dynamical variables, and you have all the information in classical mechanics. The question is, how do you find this x of t? And this x of t is find through this equation. One of the Newton equation we have, this is equal to F is equal to ma, and in classical mechanics we also learn that F is equal to minus of dv over dx, where v is your potential, and we know this acceleration can be written as the second derivative of position with respect to time. So if I combine these equation where you have this minus dv over dx and you have this F is equal to ma, you get this ordinary differential equation, or it could be a partial differential equation, but this is a second order differential equation. And if you have a second order differential equation, you would also require two conditions. In this case, it could be initial position and initial velocity. So if you know these two initial conditions and you have this differential equation, you can find x of t from this equation. So now the question is, can we replicate the same thing in quantum mechanics? Can we find such an equation in quantum mechanics? And that's exactly what Schrödinger did. He found this equation we known as Schrödinger equation, but in this case what we actually end up finding not as a function of t. Instead, you find this wave function which depend on this x and t, and this is a distribution, and this is very different from classical mechanics where we found position as a function of time. But in this case, we have this function which we call wave function, which depend on x and t. It is not giving us the information about the position, so it's very hard to find the dynamical variables like the velocity and momentum and all those kinetic energy. It's very hard to find from a wave function because this wave function is the distribution itself, and in our classical mechanics we consider particle to be localized, but this wave function is the distribution. So something that is localized should not be described by a distribution. This is a contradiction what we saw in classical mechanics, and on top of that, this is a complex function, which means if I plug in my x and t, what I get is a complex number as an answer. Something a complex number cannot define reality. So this is very mind-boggling. Like why this Schrödinger equation is giving us this wave function which doesn't seem to define reality. And this, if this Schrödinger equation does define reality, then we need to understand what this wave function is giving, what kind of physical information the wave function is giving us, and this is what we will learn more in the next video. We're going to understand how we get something physical out of this wave function. And so I hope you understand what the Schrödinger equation is. We haven't really derived the Schrödinger equation, but I do hope you understand how we get this wave function. The Schrödinger equation gives us wave function, and this wave function is complex and it's a distribution, which is very contradictory to what we saw in classical mechanics. This wave function itself, it does not have any kind of physical application, but what we're going to do is we're going to learn how we get something physical out of this. I hope you learned something about this wave function and the Schrödinger equation, what it gave us. So I hope you like this video. If you do, give it a thumbs up.